Okay, this video is to go over the notes for expected value, which is lesson 2, day 2. So in lesson 1 or lesson 2, day 1, we worked on an activity called rubber duckies and we established what expected value is and what it means to be a fair game. So in these notes for day 2, we're taking a look at a warm-up using expected value. So you're given an option of playing a game where you have to pay $1 and you're going to draw a single bill at random from either box A or box B. Box A contains one $20 bill and four $1 bills. Box B contains one $10 bill, two $5 bills, and two $1 bills. If you had $1 for playing the game, which box would you draw from and why? To make a decision, what we really should do is use expected value. So, as we were doing in class on the previous lesson, we're going to go ahead and examine the expected value of both boxes. So, what I have here is I'm going to have the probability. So, this here is going to be my probability. And this down here is going to be the amount I win. Okay, win. So, if I'm paying $1 to play, and this is also going to be, let's not forget, this is for box A. So we're examining box A right now. So if I'm drawing from box A, if I happen to draw out the $20 bill, I'm actually only winning $19 because I'm paying $1 to play. Now the probability of doing that, there's only one $20 bill in there out of 5 bills. So this would be 1 out of 5. Now, the probability of drawing a $1 bill would be 4 out of 5 because there's 4 of those in the box out of a total of 5 bills in the box. And if I'm paying $1 to play and I draw a $1, my winnings are actually $0. I'm not really losing anything necessarily, but I'm also not really winning anything either. All right, so this is for box A. So the expected value of box A is equal to 1/5 times 19 plus 4/5 times 0. And so if we come over here to our calculator, let's see, there we are. We're going to clear all that out. And if I do 1/5 times 19 and 4/5 times 0 would just be 0, my expectation here would be $3.80. So in the long run, if I did this thousands and thousands of times, on average, if I draw from box A, I'm stand to win $3.80 on average per game. Not bad. But let's examine box B and the expected value for box B. There's a few more options in box B. So again, we're going to look at the probability of the different outcomes. And I'm going to look at how much I stand to win. Now remember, we're paying $1 to play this. All right, we're paying $1 to play. So in box B, there is one $10 bill out of the 5 bills that are in the box. So again, probability of 1/5. There are two $5 bills, so that'd be 2/5. And there are two $1 bills, so that would also be 2/5. Now, if I happen to draw out the $10 bill, because I'm paying $1 to play, my winnings are actually $9. If I happen to draw out a $5 bill, because I'm paying $1 to play, my winnings are actually only $4. And if I draw out a $1 bill, because I paid $1 to play, my winnings are only $0. So that means then that my expected value for box B is going to be 1/5 times 9 plus 2/5 times 4. And then 2/5 times 0 would just be 0, but we'll put it in the calculation. I just won't type it in the calculator. So now we're going to come back to our calculator. And we're going to have 1/5 times 9 plus 2/5 times 4, and I get $3.40 as my expected value. So in the long run, if I draw from box B, on average, I'm only going to win $3.40 per game. But if I take that risk and draw from box A, and I forgot to label this as box B, so let's do that. This is box B. If I take that risk and draw from box A, on average, I would win $3.80. Now, if I'm only doing this one time, yes, there's a higher probability that I'm not going to win anything at all. But in the long run, I have a better chance of winning something on average. So remember, expected value is on average. If you wanted to win something other than $1, box B would actually be the better box to draw from, because you have a 3/5 chance of getting something more than $1, wherein in box A, you only have a 1/5 chance of getting something more than $1. So ultimately, what you should choose is box B. All right. So students are going to be tempted to do expected value, and if you do that, you're going to see that box A has a higher expected value. But what we have to stress here is that expected value is in the long run if you're playing many, many games. But if I'm only doing this once, I have a greater chance of getting more than $1 from box B than I would from box A. So you should choose from box B. All right. We did a couple of activities in class, expected value stations and casino day. And then I just want to go over some more examples of using expected value and doing a fair price. All right, so let's take a look at another example. At a carnival, you paid $1 to roll a large pair of foam dice. If the sum on the dice is at least 10, you win $5. Otherwise, you lose. What is the expectation of this game, or expected value of this game? So we're going to do the expected value here. And so I'm going to draw a table just like I did above. So let's see here. We've got this. This time it's only a single game, so I don't have to do it twice. So here in the numerator, not in the numerator, in the top of the table, I'm going to put in the probability. And in the bottom of the table, I'm going to put in what I stand to win. All right. What I stand to win or lose. Okay, so win could be in quotation marks. So when I think about a set of dice, I have to think about, well, how many ways are there to get a sum of 10 or more? And if we take a look at the sample space, what it turns out are there are 3 ways to get a sum of 10. And I would do that by 5 and 5, 6 and 4, or 4 and 6. So there's 3 ways to get a 10. There's 2 ways to get a sum of an 11, and only 1 way to get a sum of 12. So there are 5 ways to get a sum of 10 or more. All right, if the sum of the dice is at least 10. So there's 5 out of 36 ways of getting a sum of 10 or more. Now, when it comes to losing, otherwise I'm going to lose. So this is going to be 31 out of 36, because I'm either going to win or lose. There's only 2 outcomes to this game. Now, if I win and I get a sum of greater than 10, the prize is supposed to be $5, but I paid $1 to play, so I'm actually only winning $4. Now, if I lose and I don't roll a sum of 10, because I paid $1 to play, I'm actually going to lose $1. So my expected value here of this game, so expected value of dice game, is going to be equal to, and I'm going to take 5/36 times 4 plus a negative 31/36. Let's do the fraction first, times negative 1. Now let's grab our calculator and see what this comes out to be. So I have 5/36 times 4 plus 31/36 times negative 1. Remember to use your negative key on your calculator. And so I come up with about negative 31 cents. So I've got negative 0.31. I'm just going to round it to 31 cents. All right. So in the long run, if I played this game thousands and thousands of times, per game, what I stand to win or lose is 31 cents per game. All right. Now, that doesn't mean that I don't come up, roll the dice one time, and win. I could very well win and then walk away. So remember, 31 cents is not an amount I can actually win or lose in this case. It's in the long run if I played thousands and thousands of games. It's an average of what I would win or lose. So then the question comes, well, obviously $1 is not a fair price to pay to play this game because we have a negative expected value. So if you remember, fair games are when the expected value is equal to 0. The best way to solve this is to set up our expected value, but make the expected value be 0. All right, so in this game, if I do that, I'm going to have 536. That's the probability of winning. And the prize is supposed to be $5. But I'm going to say minus X. We're going to let X be the price we pay to play the game, our fair price. Then I'm going to have 31 out of 36, which is my probability of losing. And if I do lose and I don't roll a sum of 10, I'm losing all of X. And we're going to set the expected value to 0. So again, let me put this on paper. Let X equal the fair price of the game. So now I've written an equation for it. I've represented this with an equation, and now I'm going to solve it. So I would end up with 25 over 36. That's 536 times 5 minus 536x. And then I'm going to have minus 3136x is equal to 0. So all I've done here is I've distributed the 5 over 36 across the binomial 5 minus x. And then I went ahead and multiplied the 31 over 36 times the negative x, or the opposite of x. So if I solve this, I combine my x's. This is going to give me a negative x. And then I use the subtraction property of equality to bring the 25 over 36 to the other side of the equation. It's going to be equal to negative 25 over 36. Solving this, what I'm going to get is I would use my division property of equality. I'm going to have x is equal to 25 divided by 36, which isn't exactly helpful in a game like this because I want to know a price for the game. However, this turns out to be, if I were to enter this in my calculator, it turns out to be about 69.4 cents. There are some additional decimal values, but 69.4 cents is going to get us really close. You could even say 69 cents and it would get you really close to being a fair price for the game. So again, to get a fair price, take the probability of winning each different amount if there's multiple amounts. Take the prize amount, like I did here. It was supposed to be $5 minus X, so I'm subtracting my fair price. And then finally, I'll end up with my probability of losing. You're going to multiply it by negative X and then set it equal to 0 because the idea to a fair game is that the expected value is 0. And that's it. Solve the equation and you'll get your fair price for the game.